Welcome to the debate. Our focus today is on, well, a really core methodological challenge in data science. The choice between using advanced deep learning architectures and sticking with the more transparent classical machine learning models.
Right. And the central question really boils down to this. Should data scientists lean into the power, the sheer complexity handling of deep neural networks, or should they prioritize the structure and, maybe more importantly, the interpretability of traditional methods?
Exactly. I'll be arguing for the power of complexity and abstraction that deep learning, frankly, makes possible.
Okay, I see why you'd think that, but let me offer a different perspective. While yes, the performance ceiling of deep learning is often higher, I'm going to argue that simpler, more interpretable classical methods often provide a better sort of overall value proposition for most real-world applications. It's about balancing performance with transparency and, crucially, resource efficiency.
Well, let's dive into that. Deep learning architectures. They just offer superior performance, especially when you're handling really intricate pattern recognition or large sequence data. Think about specialized architectures like LSTMs. These are recurrent neural networks specifically designed to keep context over long sequences. This is absolutely essential for things like advanced time series forecasting, where subtle, long-range dependencies are key. The power isn't just, throwing more parameters at a problem. It's the hierarchy of abstraction. Each hidden layer builds on the feature extraction of the previous one. This lets the network structurally learn, going from raw pixels, say, up to recognizing high-level concepts like objects. This capacity for abstraction gives DL a huge edge when tackling genuine complexity.
That's a compelling point about abstraction, I grant you. But have you really considered the cost? I mean, while these deep networks can offer performance gains, they inherently create these, black box models. And this lack of built-in interpretability, it's a massive obstacle, especially when organizations need to satisfy regulatory compliance or audit models used for really high-stakes decisions, like in banking or healthcare. Classical methods, whether it's straightforward linear regression or tree-based algorithms you find in tools like scikit-learn, they're just often much easier for human experts to understand, to validate, and ultimately to justify. We really should adhere to the parsimony principle, Occam's razor, right? Prefer the simplest model that explains the data reasonably well, unless that complexity is absolutely demonstrably necessary. For many, maybe most, small to medium-sized data sets, these classical algorithms are perfectly sufficient and far more practical.
I'm not quite convinced that simplicity, in this context at least, is always the virtue you're painting it as. Sometimes that simplicity introduces pretty severe bias. If the true underlying relationship between your variables is fundamentally nonlinear, think about modeling complex market volatility versus simple linear trends. Proposing a simple linear model isn't demonstrating parsimony. It's fundamentally misrepresenting reality. Deep learning models, on the other hand, are capable of modeling these nonlinear situations much more naturally, often bypassing the need for tedious and, let's be honest, often incomplete manual feature engineering. And those specialized DL architectures I mentioned, they aren't just optional extras. They are explicitly needed to maximize predictive power in advanced sequence and spatial tasks, where complexity is just inherent to the problem itself.
Okay, but I just don't buy that the often marginal performance gain always justifies the astronomical complexity cost. The sheer scale of deep learning brings several really critical disadvantages, especially in operational settings. Beyond the poor interpretability, which, as I said, hinders auditability, you're dealing with dramatically high training times and, crucially, the absolute requirement for massive amounts of labeled data to prevent catastrophic overfitting. And then there's configuration sensitivity. Tuning a deep neural network, that often involves optimizing, a dozen or more critical hyperparameters? It's a process that demands immense computational resources and specialized expertise. That's quite different from setting up, say, a highly effective random forest classifier, which is much more straightforward.
You're focusing heavily on the training cost, which, yes, can be significant. But the fundamental structural capabilities of DL unlock efficiencies that classical methods simply cannot access. I'm thinking specifically here about transfer learning. The ability to take a complex model, one that's already been pre-trained on a massive data set, and then fine-tune it relatively quickly for a smaller related task, that's a capability pretty much exclusive to these layered architectures. And that can completely offset the data requirements and training costs you're highlighting, especially for organizations that can leverage these existing, powerful foundation models.
That's an insightful point regarding transfer learning, yes. Yet we also have to consider the cost of inference. Running those massive pre-trained models again and again in a production environment requires significant memory and often specialized hardware, like GPUs. That leads directly to high operational expenditure and increased latency, which can be completely unacceptable in many real-time applications. Classical ML approaches, while they generally require less memory, they're faster to execute at inference time and remain far less susceptible to this high inference cost. That often makes them the clear, pragmatic choice when operational efficiency is the priority. Look, we maintain that transparency and efficiency often outweigh potentially marginal gains in predictive power, particularly when you factor in the high operational costs, the stringent data requirements, and frankly, the real difficulty in auditing deep learning models in regulated environments.
Conversely, the ability of deep neural networks to extract nuanced, complex knowledge through that layered abstraction remains essential when the problem structure is truly highly intricate. This makes deep learning in many cutting-edge cases the unavoidable choice if you absolutely need to maximize performance in domains like state-of-the-art pattern or sequence recognition.
Ultimately, the optimal choice really demands a comprehensive trade-off evaluation. You have to acknowledge the often contradictory nature of ideal model characteristics, simplicity versus accuracy, robustness versus interpretability, as required by the specific application at hand.
Absolutely, and there's certainly more to explore in the material, particularly around the financial tipping point, where the performance gain from all that complexity actually justifies its often massive implementation and operational cost.